Hello,
Hello.
Parijata madam. Is that you?
Yes. Am I
Lenovo.
audible?
Yes, madam. Yes, madam, is Lenovo your account, madam?
Yes.
Okay, okay. Let me change the, let me rename you. Madam, I'm making you a co-host so that now you can share your PPT.
Can you see my project presentation?
Yes, madam. Yes,
Okay. Shall I start?
oh, madam. A quick intro for a 5 minutes. A very good afternoon to all the participants. I cordially invite all the participants to a 6-day online faculty development program on Next Generation IoT, the convergence of designing robust and scalable applications. Till now, we have seen the introduction of IoT, the different domains in IoT, which in engineering domain, biotechnology, and the basic sciences. And we have seen the applications, the real-time applications, the hardware security, the software security. Now it's so now how the IoT manages the data. So now I so today is the last day session of a 1 week FDP. So today's resource person, Dr. Parijata Majumdarji. It is with great pleasure that I introduce her, a distinguished academic and a researcher who has significantly contributed to the fields of science and technology. Dr. Majumdarji is currently serving as an assistant professor at the IIIT Agartala. Before this, she made an impact as an associate professor at Techno College of Engineering, Agartala. Throughout her career, she has published numerous research papers and patents in reputed international conferences and journals, reflecting her dedication to advancing knowledge in her fields of expertise. Her areas of interest are diverse and cutting edge, including artificial intelligence, the Internet of Things, 5G, blockchain, precision agriculture, cloud computing, optimization techniques, image processing, and pattern recognition. Her interdisciplinary approach exemplifies the fusion of innovation and practical application, addressing some of the most pressing challenges in today's technological landscape. With over 6 years of teaching and research experience at esteemed institutions in India, Dr. Majumdarji has demonstrated an unwavering commitment to education and mentorship. Recently, she extended her academic horizons by collaborating on a prestigious project titled, sorry, sir, sorry. She extended her academic horizons by collaborating on a prestigious project titled Materialistic Algorithms for Solving Real-World Problems with the University of Guadalajara in Mexico. As a part of postdoctoral research, Dr. Mazumdar's excellence in research has not gone unnoticed. She has been selected for the esteemed EARG Award 2024 for excellence in research and development in association with the Math Tech Thinking Foundation, India. This recognition underscores her remarkable contributions to innovation and knowledge dissemination. Beyond her research and teaching roles, Dr. Majumdar is an active expert speaker, reviewer, and editorial board member for several reputed international journals and conferences. Her influence and expertise extend globally, where she is respected as a thought leader in her domain. Please join me in applauding and celebrating the remarkable journey and achievements of Dr. Parijata Majumdarji, a true visionary in her field. Now I request the coordinator of this faculty development program, Dr. E. Govind sir, HOD of head of the department is ECE. Now I request sir to invite the resource person. Over to you, sir.
Good afternoon to today resource person, Dr. Parijatam Majumdar, and my dear participants, on behalf of EC Department and Avanti Institute of Engineering Technology. So I heartily welcome you, madam. And today is the 7th day of this FDP. And so on that day, we are closed this session. So with this expert to talk from the Madam Parijata Majumdar. So on topic data management and big data analytics in IoT. Thank you for madam for accepting our invitation. And on behalf of Avanti Group, we are all welcome you, madam. Thank you.
Thank you very much, sir, for your warm and cordial welcome to me. So today my topic of discussion is data management and big data analytics in IoT. So this is the brief outline of my presentation. I'll rather start with introduction, where I shall be discussing the overview of IoT, importance of data management and analytics in IoT. Also, next I will discuss data collection, data transmission, data storage, data analysis, and data visualization as a whole lot of part of integration of IoT data lifecycle. Then I will be shortly discussing the data management challenges in IoTs and what will be the best strategies and practices following this. Then I shall be discussing the big data analytics in IoT, role of big data, what are the different techniques and algorithms, techniques, real-time versus batch processing. Then I shall be discussing how IoT can be integrated with data management and big data analytics, and how to make this IoT data architecture very much scalable. And I shall be discussing different frameworks and architectures related to this. And then I shall be discussing how cloud computing has moved so far to the edge computation, and how AI and machine learning techniques are playing a key role in IoT analytics. Then shortly I shall be discussing the case studies and applications in IoT, industrial IoT, and predictive maintenance. Then I shall be discussing the future trends and the emerging research directions, different challenges and opportunities in this data management and big data analytics using IoT. Am I audible, sir?
Yeah, audible, madam.
Okay. Are my slides visible?
Yeah, visible.
Yes, madam.
Okay. So let us start with what is an IoT. IoT refers to the network architecture of interconnected devices that collect, exchange, and act on data. Now, how can this data be collected? This can be from different smart thermostats, from fitness trackers and different industrial sensors, and different even precision agriculture sensors like temperature, humidity, etc. The ecosystem of IoT is very smart, which consists of devices and sensors that capture data from the environment. The connectivity is done with networks like Wi-Fi, 5G, and Bluetooth. And the different platforms in the ecosystems of IoT includes cloud or edge platforms for data storage and processing. Now, the main question is why data actually matters in IoT. IoT, since is a real-time collection of data
Sorry
from
for
different
interruption,
sources.
madam. Please, slides not moving. Resume slides slow.
Sir, is my slides visible now?
Okay, madam.
So data actually matters in IoT because IoT generates massive volumes of data that drives decision making. Without efficient data management, insights cannot be derived effectively. So challenges without proper management of data includes data overloading in the network, which results in poor quality and inaccessible data, reducing the IoT's value. So the relationship of IoT and big data includes checking what data has been gathered, adjusting the data as per user requirements, planning what can be the next sequence of actions, how data can be processed from raw data to information, and then performing the user task. And big data, on the other hand, utilizes several data analytics techniques like artificial intelligence, data-based learning, big data, capturing, storing, and analyzing of data, and collecting of the data from the Internet of Things. So IoT devices generate high volume, high velocity, and high variety of data. These are the 3 V's of big data and the core attributes of big data. So the IoT how benefits from big data include scalability that handles IoT's data growth, advanced analytics that enables machine learning and predictive insights derivation from the data. IoT data can be collected from a wide variety of sensors which are capable of collecting real-time data. The different tools includes IoT platforms and data ingestion, that is AWS IoT Core, which manages device communication, collect data, and routes it from storage and analysis. Then Google IoT Core, which provides device management, secure communication, and integration with Google Cloud Service. And the next is Azure IoT Hub, which enables bidirectional data communication and data ingestion. Not only this, IoT uses several protocols for data collection. One of the famous protocols is MQTT, Message Queuing Telemetry Transport, which consists of lightweight protocol ideal for constrained devices. The next is Constrained Application Protocol, which works over UDP, that is the User Datagram Protocol, which is specially suitable for small and low power devices. And the different techniques that the big data it utilizes are edge computing, where data is pre-processed closer to the source to reduce latency and bandwidth usage. And then comes the event-driven architecture, which efficiently handles and processes real-time data streams.
I'm sorry for the interruption. The slides are not moving, man.
So the data storage tools and techniques mainly consists of storing the data, IoT data, that requires systems that can handle high volume and variety effectively. The tools mainly include the cloud storage techniques such as AWS, that is Azure Web Service S3, Google Cloud Storage, Azure Blob Storage, which are nothing but scalable storage solutions for structured and unstructured IoT data. IBM Watson platform is another popular platform which provides integrated data storage with analytical capabilities. Edge storage solutions, fog computing platforms, open fog consortiums promotes frameworks which is suitable for storing data closer to the devices. Also, edge storage solutions consists of several databases that includes time series databases like Influx, Timescale, which is used for optimizing the timestamp data. Then comes the NoSQL database, which typically consists of MongoDB, which is suitable for unstructured and semi-structured data. SQL databases traditionally can also be used, which mainly includes PostgreSQL and the MySQL techniques for structured data with relational models. Then comes the techniques of data compression. It reduces the size of stored data while preserving its integrity. Then comes the technique of partitioning. It improves the query performance by dividing the data across nodes or storage units.
Partitioning improves query performance by dividing the data across nodes or storage units.
Then comes the big data in IoT context. IoT devices generate high volume, high velocity, and high variety of data, which are mainly the core attributes of big data. Then comes the data analytics and the data visualization tools. Analytic tools transform raw data into actionable insights. The tools mainly includes Tableau and Power BI. Power BI is of course used for making beautiful presentations, as I've used today, creating interactive dashboards and reports. IoT analytic platforms also includes AWS IoT Analytics and Azure Stream Analytics. Several machine learning platforms has also came into being, such as TensorFlow and PyTorch, which are specially suitable for creating deep learning models. And the concept of deep learning has come from the concept of big data. As long as the 3 V's of big data, that is the volume, veracity, and variety increases, the need for deep learning models also increases. Then comes the techniques of descriptive analytics, which summarizes past IoT data to identify trends. Then comes the concept of predictive analytics, which uses historical data to predict future outcomes. Prescriptive analytics comprises of recommending action based on analytics when done using predictive and descriptive analytics. Then comes data collection, which consists of different devices generating different types of raw data. The data are not at all homogeneous, they are heterogeneous. They have come from different sources. So data types can be of several, such as environmental data, for example, temperature, humidity, biometric data, for example, heart rate, and operational data, which consists of machine status. Tools and techniques such as sensors and actuators, where devices that monitor and interact with the environment. IoT protocols uses MQTT and QoEP, as I have already discussed. Bluetooth and Zigbee networks are used for data transfer. The challenges here in data collection is ensuring data accuracy. Since the data are coming from heterogeneous sources, the data can be inaccurate or noisy sometimes. So we have to manage and take care of managing diverse formats and sources. Then comes in the IoT data lifecycle, the phase of data transmission. After the data is collected, data is transmitted to processing systems via networks. For this purpose, we utilize MQTT, which is lightweight, suitable for low power devices, constrained access protocols, which is efficient for resource constrained IoT devices, and HTTPs, which are commonly used but obviously resource intensive. So in IoT, we mainly utilize MQTT and sometimes constrained access protocols in resource constrained IoT devices such as Bluetooth. There are different network types, which includes Wi-Fi, 5G networks, LoRaWAN, and Zigbee. And now even the 6G network architecture, the high speed and high bandwidth architecture has came into fore. The main challenges in the data transmission phase includes the managing the latency and the bandwidth and ensuring secure data transmission so that the data does not suffer man-in-the-middle attack and other brute force attacks. Then comes the phase of data storage, where the data is stored in the cloud, edge, or hybrid systems. The storage options mainly includes the cloud, which is highly scalable and centralized, and the edge storage, which is localized storage near the data source, which is mainly designed for the purpose of reducing latency. Then comes the database types, which consists of SQL databases for structured data, NoSQL databases for flexible storage of semi-structured and unstructured data, and the time series database, which is optimized for timestamp data. An example of time series database can be influx database. In this phase, in the data storage phase, the main challenge is balancing the scalability with cost incurred and selecting storage solutions based on use cases, that is as per user requirement. Then comes the data processing phase, which transforms this raw data into usable formats meaningful enough for deriving the information. Here comes different types of processing, such as batch processing, where stream processing and edge computing. Batch processing includes analyzing the large data sets at scheduled intervals. Okay, batch processing deals with analyzing the data sets at scheduled intervals. For example, Hadoop. Hadoop is a big database where large data sets are analyzed at scheduled intervals. Then comes the stream processing techniques, where real-time data processing are utilized for immediate insights. For example, Apache and AWS. And edge computing are also utilized for data processing, where data are processed locally to reduce latency and bandwidth usage. The main challenge in this phase includes handling real-time processing for high-velocity data, ensuring the quality of processed data, data analysis. The techniques includes descriptive analytics, which summarizes historical data, predictive analytics, which utilizes machine learning based prediction techniques to predict future outcomes, and the prescriptive analytics, which recommends actionable solutions. Data visualization mainly includes presenting insights through dashboards and reports, and data retrieval and deletion includes retaining or deleting the data based on policies. Here different policies are used, such as retrieval, which retains historical data for long-term trends and regulatory compliance. Then comes the deletion, which removes redundant data to reduce storage costs. And here is a challenge which comprises of ensuring the regulatory compliance, for example, GDPR and HIPAA. It decides on retention policies. Then comes what are the challenges in IoT data management. The first and foremost challenge, which actually bothers the IoT data management service, is scalability. The main issue is that the IoT generates massive volumes of data, which grows as more devices comes online. The impact is that systems must scale to store, process, and analyze these ever-increasing data sets. For example, managing sensor data from millions of devices in a smart city. The second challenge is data heterogeneity. For example, data that is collected from video streams, the impact is that it ensures interoperability between devices and platforms that becomes complex with growing data. Example is combining data from IoT-enabled cars, weather sensors, and traffic cameras. The third example is data security. IoT systems are often vulnerable to cyber attacks like data breaches, device hacking, and eavesdropping. The main impact is unauthorized access to sensitive data that can lead to financial and reputational damage.
Hacked IoT devices in healthcare exposing patient information can be a buying example of
data security, how it is impacted in IoT
data
data
management.
management.
The next example is data privacy. The data privacy,
IoT devices collect personal and sensitive data, raising privacy concerns. It impacts non-compliance with regulations and can result in legal penalties. Examples of data privacy service includes wearable fitness trackers storing users' health metrics. The next is real-time processing. The main issue is that many IoT applications require low latency data processing and decision making. The processing of high velocity data streams in real time can be overwhelming in infrastructure. So the main example here is autonomous vehicles relying on real-time sensor data. For example, autonomous cars that are often seen in USA. Then the next issue is data quality. IoT data may be incomplete, noisy, as I have already said, or redundant in nature. It mainly happens when sensor data are applied, for example, in a precision agricultural field, okay, and the data sensors are not located in a far away place. Then they will result in gathering the same or redundant data. The impact will be poor data quality that can degrade analytics accuracy and decision making. The examples are faulty sensors sending inaccurate temperature readings. The next challenge is cost and resource constraints, which involves managing IoT data requires significant computational resources and storage capacity. The small-scale IoT implementations may struggle with high operational costs. Examples are startups unable to afford cloud infrastructure for IoT data. Now, what is centralized versus decentralized data management? IoT ecosystems often adopt centralized or decentralized approaches for data management, with each of its have its own advantages and trade-offs. Centralized data management includes where all the data is collected and managed in a single location, typically a cloud server or centralized data center. The advantage is simplified management and maintenance, easier implementation of security services, and unified analytics. Then what can be the possible challenges for centralized data management? The challenges are when the high latency is requirement for real-time applications, and there is often a single point of failure. I want to re-emphasize there is a single point of failure. For example, if the central server goes down, then centralized data management will be impossible. Expensive bandwidth and cloud storage costs are the different other challenges. So several use cases for centralized data management includes cloud-based IoT platforms for global monitoring and analytics. Then comes the decentralized data management. Here data is processed and managed closer to the source, such as the edge of the network or within the distributed nodes. The advantages can be reduced latency for real-time decision making, better bandwidth utilization by filtering data locally, increasing resilience with no single point of failure. Then what can be the possible challenges? The possible challenges can be higher complexity in managing distributed systems, potential for inconsistent data across nodes, and greater difficulty in implementing global analytics. The use cases are industrial IoT systems using edge computing for real-time control, smart grids analyzing local energy consumption and generalization, and choosing between centralized and decentralized models is obviously sometimes difficult. So centralized data management techniques are particularly suitable for applications requiring global insights or retrieval of large data sets. For example, enterprise level analytics. And decentralized data management techniques, on the other hand, are ideal for latency sensitive applications such as autonomous vehicles, predictive maintenance, and healthcare monitoring. So centralized models are suitable for enterprise level analytics, and decentralized models are, on the other hand, suitable for predictive maintenance and healthcare monitoring. So what is the role of big data in IoT? Big data plays a crucial role in enhancing the capabilities of IoT systems by enabling the processing, storage, and analysis of the vast amount of data generated by connected devices. Here is how big data complements IoT. Handling IoT data volume, velocity, and variety. Volume includes IoT devices generates massive amounts of data daily, and big data tools provide scalable solutions for this data storage and processing. For example, data from smart meters, industrial sensors, or connected vehicles. Velocity, IoT data streams arrive in real time. Big data technologies process this data swiftly for timely insights and timely action. For example, real-time traffic updates in smart cities. Then the last one is variety. IoT data is often unstructured or semi-structured in format. Big data supports handling these diverse data types. Then the next is real-time analytics for IoT. Big data tools enable real-time analysis, ensuring actionable insights that are available without delay. Example, monitoring machine performance in industrial IoT to predict equipment failure. The next one is predictive and prescriptive analytics. Predictive analytics, big data utilizes machine learning algorithms to predict future events based on historical IoT data. For example, predicting energy demand in smart grid. The next one is prescriptive analytics, where actions are suggested to optimize performance and prevent issues like dynamic routing optimization for delivery vehicles. For example, we often order foods from Swiggy, Zomato, and likewise services. Here, prescriptive analytics are used as big data techniques in IoT for suggesting actions to optimize processes or prevent issues. And it helps in dynamic routing optimization for delivery vehicles. The next one is data integration and interoperability. Big data platforms integrate diverse IoT data sources into unified systems, simplifying interoperability and ensuring seamless communication between devices. Example includes a smart home hub connecting and managing data from multiple devices, for example, thermostats and security systems. The next issue is scalability and cost efficiency. Big data technologies like Hadoop and cloud solutions like AWS and Azure provides cost-effective, scalable infrastructure for storing and analyzing IoT data. And then, last but not the least, it supports enhanced decision-making capabilities. Big data analytics empower IoT systems with actionable insights, enabling informed decision-making in real time or through deep analysis. Examples include smart agriculture systems analyzing weather and soil data to optimize irrigation schedules and giving real-time weather station-like views. Here is a comparison showing how real-time processing can be differentiated from batch processing of data. The first and foremost aspect is timing. In real-time processing, data is available on time, but in batch processing, the data is available on delay, that is scheduled intervals. Typical use case in real-time processing may include time-sensitive applications, and in batch processing, it includes historical or large-scale analysis. In real-time processing, we utilize tools like Storm, AWS, Kinesis, etc. And in batch processing, we utilize big data techniques like Hadoop, Spark, etc. There is a separate course on Hadoop and Spark in big data analytics subject. And now coming to the cost aspect, here high computational cost is incurred in real-time processing. And in batch processing, cost is efficient for large data set. Infrastructure-wise, real-time processing requires robust real-time systems, whereas batch processing can use simpler storage and computation. Example typically includes traffic monitoring and stock trading in case of real-time processing, and in case of batch processing, it includes yearly sales report and trend analysis. Now, how shall we optimally choose between real-time and batch processing? Real-time processing will be used when there is use cases that demands immediate responses. For example, healthcare, autonomous systems, or fraud detection in banking services. And that time we would be requiring real-time processing. Then batch processing. Batch processing is suitable for applications where latency is acceptable, such as data trend analysis or large-scale periodic reporting. So these are the different big data analytics architecture. The common architecture is Lambda architecture. It combines batch processing and real-time processing for comprehensive data analytics. The different layers include batch layer, which stores and processes historical data, for example, Hadoop and Spark. The next layer is speed layer, which includes processing real-time data streams, for example, Kafka and Storm. And the last layer is serving layer, which combines results from batch and speed layers for end user access. Typical use cases include smart grid systems analyzing historical and live power usage. The next common architecture is Kappa architecture. Its purpose is to simplify data processing by focusing on real-time analytics only. The main components of Kafka architecture includes streaming platforms like Kafka or AWS Kinesis, processing engines like Flink or Spark streaming, use case which includes autonomous vehicles requiring low latency decision making, etc. The third one is microservices architecture, where the main purpose is to develop a modular architecture where individual services handle specific IoT tasks. The main features of microservice architecture includes each microservice is independently deployable and scalable. It facilitates integration with APIs or application program interface for device and data management. Typical use cases includes smart home systems with separate services for lighting, security, and HVAC control. So, how IoT data management and big data analytics all can be integrated seamlessly. The first and foremost concern for this integration includes designing and development of IoT frameworks like AWS IoT Core and Google IoT Core that manages the data collection. Protocols typically include MQTT and CoAP that handles low latency communications. Then comes the data storage, where frameworks like Hadoop and cloud storage solutions ensure scalable data storage. Then comes data processing, which utilizes big data frameworks, for example, Spark, that analyzes IoT data in batch or real time. Analytics and insights. Advanced analytical platforms, for example, Power BI, which is used to develop a beautiful presentation, can help us in generating insights from the data. Machine learning models, example, TensorFlow, PyTorch, enable predictive and prescriptive analytics from the data. Now, concerning this different aspect of edge computing and cloud computing, we'll see how the cloud computing is moving towards edge computing nowadays. Here, the processing location is local. That means that in edge, the data is computed near the data source. And in cloud computing, the data is centralizedly processed in remote servers. Latency in case of edge computing or real-time processing is low, whereas in cloud computing, the latency is high, which incurs a lot of data transmission delays. As far as scalability is concerned, edge computing is limited to local device capabilities, whereas in cloud computing, scalability is virtually unlimited. If you have cloud data storage, then your scalability is unlimited. Then in case of bandwidth usage, it is low, which processes data locally, and in case of cloud computing, bandwidth is high, which transmits raw data. In case of edge computing, security is improved, which involves local processing only, whereas in cloud computing, since the scalability is virtually unlimited, so there is potential exposure to cyber risk. Computational power. In case of edge computing, the computational power is constrained by device hardware, whereas in case of cloud computing, the computational power is high, powered by data centers. As far as use cases are concerned, real-time analytics and critical applications typically utilizes edge computing, whereas large-scale analytics, archival, and machine learning models utilizes these use cases in cloud computing. So this is how IoT devices are gaining popular attention nowadays, and these are the network devices where IoT devices are collecting real-time data and transmitting those data over the network, and the IoT gateway is responsible for storing those networked data into the cloud storage, and the data is accessed from the cloud using big data analytics techniques and big data pipeline such as Apache Spark to draw meaningful insights from IoT data as output. So this is how integration of IoT with big data analytics for the development of smart society is taking place. Edge and cloud computing together. Many IoT systems nowadays adopt a hybrid approach that combines the strength of edge and cloud computing. Example use cases typically includes autonomous vehicles, such as real-time processing of sensor data for driving decisions, cloud techniques, which is responsible for storing trip data for training AI models, smart cities, which stores data on edge devices, where local processing for traffic lights and emergency systems are done, cloud data, which is aggregated for long-term urban planning, industrial IoT, industrial IoT, where data is mainly processed in edge computing based techniques, where real-time monitoring is applied for predictive maintenance. And in cloud, it utilizes enterprise-wide analytics and reporting. Now the main concern remains when to use edge computing and when to utilize cloud computing. We'll use edge computing when we require real-time services and in latency-sensitive applications. In areas with limited or intermittent internet connectivity, we'll utilize edge computing. And in case of privacy-sensitive applications also, we will utilize edge computing. And in case of cloud computing, we shall use cloud computing when we require it for large-scale analytics and machine learning, scenarios that requires high computational power. It is suitable for archival, big data archival, compliance, and global insights. So as you can see in the following diagram, in the edge computing, computation takes place locally near to the data source. Whereas in case of cloud computing, data computation mainly occurs in the virtual cloud, where the scalability is unlimited. Now coming to the role of AI and machine learning in IoT analytics. Artificial intelligence and machine learning improves IoT systems in several different ways. For example, predictive analytics that anticipate future events or trends based on historical and real-time IoT data, which examples include predictive maintenance in manufacturing to reduce downtime, forecasting energy demands in smart grids. Anomaly detection, which involves identifying the outliers or irregular patterns in IoT data streams. Examples include detecting cybersecurity threats in IoT network and identifying faulty sensors in smart home systems. Automation and decision making. It automates tasks and support decision making based on data insights. Autonomous vehicles making navigation decisions, smart thermostats optimizing energy usage are some of the examples. The real-time processing includes analyzing and acting on IoT data in real time. Examples include monitoring patient vitals in healthcare systems for instant alerts, managing traffic flow in smart cities based on live traffic data, and natural language processing that enhances human interaction with IoT devices utilizing voice or text. Examples of natural language processing techniques are voice controlled assistants like Alexa, which is now a part and parcel of everyone's home, right? I know many of the participants are already utilizing these Alexa techniques in their home, or chatbots managing IoT-enabled customer service systems. Now, the key applications of artificial intelligence and machine learning in IoT includes smart cities. Several use cases can be seen in utilizing of smart cities, where traffic management is a concern, which utilizes real-time traffic data and artificial intelligence algorithms. Waste management, optimizing collection routes based on sensor data can also be a possible use case. The second use case is industrial IoT, IIoT. Quality control through machine learning driven defect detection in production lines, asset performance monitoring for predictive maintenance are the typical use cases of IoT. Smart home use cases includes AI-enabled security systems detecting unusual behavior or intrusions. Smart appliances learning user preferences for energy efficiency is another typical use case for smart homes. The next one is healthcare IoT. Use cases mainly include continuous health monitoring utilizing wearable devices, AI-assisted diagnosis based on sensor data and medical records, and agricultural IoT, which utilizes precision farming with AI models prediction, irrigation needs, pest detection utilizing ML models analyzing drone images. So these are the certain and smart applications of utilizing AI and machine learning in IoT, which includes smart cities, industrial IoT, IIoT, smart homes, healthcare IoT, and agriculture IoT. Now, what can be the possible challenges of AI and ML integration with IoT? Number one is data quality issues, which consists of incomplete or noisy IoT data collection that can reduce machine learning model accuracy. Scalability, which includes processing and analyzing data from billions of devices requiring significant resources. Third one is latency, which includes real-time applications demand low latency processing, challenging in edge or distributed environments. The next one is security concerns. Machine learning systems in IoT networks are vulnerable to data poisoning and adversarial attacks, such as man-in-the-middle, denial of service, distributed denial of service, etc. The next one is model deployment and updates. Deploying and updating machine learning models across distributed IoT devices can be complex, as the number of IoT devices and the data volume, veracity, and variety are increasingly demanding day by day. So this is the relationship among IoT, big data, and cloud computing. At first, data has been acquisition has been done. Then data has been subscripted from the cloud database, and then the device management is also done sideways. The device management from the cloud database typically includes transforming, loading, and extracting. That is the ETL process of the database is done for big data analytics and for persistent data storage. Here, artificial intelligence, where data-based learning is typically done. So this is the technique of information security and the relationship among IoT, big data, and cloud computing. The main concern is managing the volume, variety, and velocity of big data while acquiring data from IoT in a secured manner and processing the same data in cloud computing, such as Amazon Web Service, etc. The next is future of artificial intelligence and machine learning in IoT. Federated learning. I don't know how many of you have already came across the terminology of federated learning. It has been an immersive research topic in the year 2024, the federated learning. Here, artificial intelligence models are trained on distributed devices to enhance privacy and reduce data transmission to the cloud. Here, autonomous IoT systems are continuously being built where AI-powered IoT ecosystems that operate independently with minimal human intervention is done. Explainable AI, enhancing transparency in ML models to increase trust in AI-driven IoT analytics is done. The explainable AI deals with the main thing that AI is actually typically a black box, and it adds explanation to the black box, where data, starting from the data gathering to data processing, everything is explained using explainable AI algorithms. Nowadays, all these are integrated with 5G networks, of course with 6G networks now even, where high-speed connectivity is ensured, enabling real-time AI-powered analytics at scale. So these are the few of the case studies and applications of IoT and AI with AI and machine learning. IoT combined with AI and machine learning transform industries by delivering intelligent real-time solutions tailored to specific use cases. Some of those use cases are smart cities, healthcare, industrial IoT, and predictive maintenance. For example, if you take the case study of a Barcelona smart city initiative, you can Google it for this. The main challenge is to improve the urban living conditions by optimizing resource utilization and city services. What can be the probable solution? Barcelona implemented different IoT sensors and AI algorithms for enabling smart parking of cars that utilizes several real-time sensors to guide the drivers to available spot. Several real-time sensors are utilized for developing a smart parking system so that they can easily manage the traffic in Barcelona. Intelligent street lighting is also implemented in Barcelona, as you can Google and see, that are adjusted based on activity levels. Waste management systems that can optimize collection routes based on bin fill levels is another solution which Barcelona Smart City Initiative has adopted. So the main impact is reduced traffic congestion by 30%, as there are real-time sensors which automatically alert the users that when there will be traffic or when the color of the traffic light will changing from yellow to red or from green to yellow. So it will reduce the traffic congestion by 30%, decreased energy consumption in street lighting since it is adjusted based on activity levels. For example, in night time, the energy consumption in street lighting is required, whereas in daytime, street lighting is not at all required. That means utilizing these real-time IoT-based sensors in Barcelona Smart City Initiative, they have decreased the energy consumption by 37%. The next is optimized waste collection routes that saved significant operational costs. Waste management systems that are employed in Barcelona, it saved significant operational cost based on bin fill levels. Another case study in case of healthcare is Medtronic's remote patient monitoring. The main challenge in this Medtronic remote patient monitoring is that it provides real-time health monitoring for chronic disease patients. That means the patient disease is not acute, it's chronic. They adopted solutions based on IoT-enabled devices that collect vital parameters, for example, heart rate, blood pressure, and so on. AI algorithms are also used that detect anomalies, triggering alerts for healthcare providers. What is the impact of this Medtronic's remote patient monitoring system? It reduced hospital readmission rates by 50%. Since, for example, if the heart rate is suddenly increased, then the pulse rate will also be increased, and there will be an automatically alert system generated by the IoT devices. Hence, they can predict the emergency situation beforehand. The patient vitals goes on deteriorating. So, timely intervention in hospitals has been adopted by this Medtronic's remote patient monitoring systems. And not only this, the patient outcomes are also improved through these timely interventions, and we can save patient life utilizing these IoT-enabled devices. Many of the smartwatches have now been developed, which actually shows your blood pressure, temperature, humidity level, your pulse rate, everything that we used to wear. This is an example of wearable sensor which we used to wear at hand. For example, fitness trackers and health monitors that collect real-time patient data. For example, how many kilometers we have walked per day. For example, Fitbit, Apple Watch, and other wearable devices that uses IoT to track health. Several AI-assisted diagnoses are also there, which utilizes machine learning models that analyze IoT-generated healthcare data for early disease detection. Obviously, the disease detection will be at early stage because they are continuously monitoring heart rate, blood pressure, etc. So before the emergency occurs, they will show that there is an alert. For example, IBM Watson diagnosing cancer using patient records and IoT devices. IBM has already utilized these AI-assisted diagnosis. Even medical practitioners and professionals are nowadays replaced by robots. Obviously, they cannot predict your real-time situation just like as doctors, but now research has been going on how to replace these medical practitioners and how to develop an AI-based medical hospital replacing manforce. So telemedicine is also another important topic in the healthcare, where IoT device enable remote consultation and monitoring with AI-driven analytics. Example includes Vital Connect's IoT patch for remote ECG monitoring. Next comes the industrial IoT. GE's Brilliant Factory is a case study where the main challenge is improving the manufacturing efficiency and reducing the downtime of machineries in factories. They have to reduce the downtime of machineries and have to also improve the manufacturing efficiency. This is the use case for GE's Brilliant Factory. You can Google it. The main solution they have adopted for this is that they utilize several IoT data sensors to track machine performance in real time. AI and machine learning algorithms analyzes sensor data to predict equipment issues and optimize production schedules. What is the impact then? The possible impact is that here it improved production efficiency by 25%, it reduced maintenance cost by 30%. That means GE's Brilliant Factory utilizing these IoT sensor track and AI and machine learning have already improved production efficiency by 25% and reduced maintenance cost, that is downtime of machineries, by 30%. The real-time application of this is IoT and AI drive autonomous manufacturing robots. For example, Fanuc robots utilizing IoT data for adaptive production. Quality control is another application where machine learning powered vision systems inspect products for defects in real time. Example is AI in Tesla's gigafactories is utilized for quality assurance. The next application is supply chain optimization. IoT data integrated with AI improves inventory and logistic management. Example is DHL using IoT and AI to predict supply chain disruptions. The next is predictive maintenance. An important case study here is Rolls-Royce aircraft engines challenge. It reduces engine downtime and maintenance cost in aviation. The main solution in that is IoT sensors on engines monitor parameters like temperature, vibration, and pressure. Here AI analyzes this data to predict failure before they actually occur. So downtime prediction of machineries and prediction of failures beforehand are made possible utilizing these IoT devices. So what is the impact? Again, the impact is reduced unplanned maintenance events by 50%. As long as the machine learning can predict the downtime of machineries, the maintenance events will be obviously reduced. And in this case study, it is reduced by 50%. It saved millions of dollars in operational costs for airlines. What is the application then? Machinery health monitoring. IoT and AI detect anomalies in factory machineries to schedule repairs. For example, Siemens MindSphere is utilized for industrial equipment. The next application is fleet maintenance, where IoT sensors are deployed on vehicle tracks wear and tear with AI recommending service schedules. For example, uninterrupted power service utilizing predictive analytics for its fleet. This is an example of fleet maintenance, where UPS utilizes predictive maintenance for its fleet. The next is energy system maintenance. AI can predict real-time failures in wind turbines and solar panels utilizing IoT data. It can be exemplified in the case of General Electric Predicts platform for energy systems. So these are the applications of predictive maintenance in real-time scenarios for machinery health monitoring, fleet maintenance, and energy system maintenance. The next is what are the key benefits that we have gathered so far by combining IoT with artificial intelligence and machine learning. It has a transformative impact that has been demonstrated across several sectors. In case of smart city industry, it reduces congestion, optimized resource usage, and enhanced citizen safety. In case of healthcare, it has improved patient care, reduced operational cost, and has provided us with real-time health insights. Industrial IoT. In case of industrial IoT, IoT combined with AI and machine learning enhanced efficiency, automated processes, and reduced downtime of real-time equipments. In case of predictive maintenance industry, the main key benefit is that it offers lower operational cost, minimized unplanned downtime. That means a machine will not be surprisingly fail on its own. It will be alerted by the IoT devices beforehand. And also prolonged asset lifespan. As we will be planning the timely maintenance activities, the asset lifespan will be prolonged. The next is the future trends in IoT, AI, and big data analytics. The first emerging technology is 5G and beyond. Research has shown that ultra low latency and high bandwidth will enable seamless IoT connectivity which supports smart cities, autonomous vehicles, and industrial automation. Examples typically include smart factories leveraging 5G for real-time machine communication. Another emerging technology is edge-based artificial intelligence algorithm. Here, AI models are deployed directly on IoT devices, edge computing that will enable real-time analytics and reduce reliance on cloud infrastructure. For example, autonomous drones performing image analysis on devices. Drones and UAVs, that means unmanned aerial vehicles, are utilizing these emerging technologies of edge-based artificial intelligence, which performs image analysis but on device. Blockchain is another emerging technology in AI, which ensures that secure decentralized data exchange among IoT devices is made possible that comprehends trust and reduces fraud risk. Examples mainly include supply chain systems that utilizes blockchain for transparent tracking. Supply chain systems can utilize this blockchain for transparent tracking, which is nothing but mainly a form of distributed ledger. A lot of blocks are there which actually consists of the data and the key, that where each of the key along with the data will be connected by means of blocks, and this is nothing but a distributed ledger. Then next comes the quantum computing. Quantum computing will enhance the speed and complexity of IoT data analytics, especially for optimization problems. Example, quantum-based traffic management in smart cities. Quantum-based traffic management in smart cities will enhance the speed and complexity of IoT data analysis, especially for optimization problems. The next is digital twins. Digital twins create virtual replicas of physical systems, which allows real-time monitoring, simulation, and predictive data analysis. Example is Boeing, utilizing digital twins to monitor aircraft performance. In aircraft, Boeing is done utilizing digital twins, which are nothing but replicas of real-time twins or physical systems. IoT interoperability and standards is also there, which utilizes emerging frameworks like Matter that aims to unify communication protocols for seamless devices integration. IoT interoperability standards, mainly examples include smart homes using interoperable IoT systems for lights, thermostats, and security. In the current year of 2024, I have wrote a paper, Digital Twins and Integration of Blockchain for IoT data analytics, and it has been accepted in a ACI indexed journal with an impact factor of 8.1, that is Computers in Industry. You can Google it and check my publications. So the next one is challenges. What are the different challenges? Data privacy and security is one of the main challenge, where IoT network generates vast amount of sensitive data, making them attractive targets for cyber attacks. The solution can be enhanced encryption, blockchain integration, and secure firmware updates. The next challenge is scalability issues. Managing billions of IoT devices while ensuring seamless data integration is a complex task. One of the main solutions is cloud edge hybrid architecture, where in edge the scalability is obviously unlimited, but in edge local data processing can be done. So we can utilize this cloud edge hybrid architecture for managing the scalability issues of millions of IoT data devices. And we can also obviously, of course, utilize distributed computing models. The next challenge is energy efficiency. Powering IoT devices, especially in remote areas, remains a challenge. In remote areas, the network with high bandwidth and high latency is almost impossible. So powering IoT devices and its scalability remains an open challenge. So the solution can be the advancement and utilization of low power IoT devices and energy harvesting techniques. Low power IoT devices we can do this using LP1 techniques. That means low power wide area networks and energy harvesting techniques like utilizing duty cycling for sensors. That much we can adopt for managing these IoT devices. I have a publication in this wireless personal communications and networking in green IoT technologies, where you can obviously surf the Google net and can check how energy efficiency of IoT devices can be done using green IoT techniques. There are several green IoT sensors, and how data management can be done using constrained access protocols are widely being discussed in the paper. You can surf the internet with my name and can check the green IoT that has been published in wireless personal communications in the year late 2023. The next challenge comes the data silos and interoperability. Proprietary systems often create data silos, limiting the integration of IoT with big data analytics. One of the burning solution can be adoption of open standards and application program interface for cross-platform communications. The ethical concerns can be the use of AI and IoT that raises concerns about surveillance, bias, and decision-making transparency. How to provide solutions for these ethical concerns? We can develop, of course, explainable AI techniques and adherence to ethical AI guidelines for solving this ethical concern problem, as explainable AI is mainly utilized to comprehend the black box AI. Whenever the machine learning models are utilized and complex data processing is being done, we can utilize this explainable artificial intelligence algorithm for solving this black box problem. Some of the explainable AI algorithms can be shaped. You can just Google and check. The next one is opportunities. What are the different opportunities for big data analytics in IoT? The first one is industry-specific transformation. IoT and AI offer opportunities to redefine industries such as in healthcare, transportation, agriculture, and retail. The examples can be precision agriculture, where several real-time IoT sensors have been employed for efficient water and fertilizer usage. We can also plan irrigation schedules based on this real-time data. The next is sustainability initiatives. IoT can monitor and optimize energy consumption, supporting green initiatives, that is green IoT, and reduce carbon footprints at the same time. because the sensors data that are utilized in real time emits a lot of carbon, which is not at all suitable for our environment. So to make our environment green again, we have to utilize these green sensors and utilize the duty cycling like techniques for the existing sensors. Example can be smart grids utilizing IoT for energy distribution based on demand. And the next one is enhanced customer experiences. AI-powered IoT systems can deliver personalized real-time experiences where AI-driven real-time systems that recommend products based on in-store behavior. Economic growth. IoT adoption is expected to add trillions of people to the global economy. It can create jobs and business opportunities, but at the same time, it has not only boon, it has base too. That means a lot of robots, AI based robots, are already replacing the medical practitioners and several engineers and professionals in different IT companies. So what can be the probable solutions? We made robots for utilizing them, but in turn we are ourselves getting replaced. So we have to take care on these also. Examples can be IoT-enabled system startups developing solutions for logistics and smart homes. The next one is real-time data monetization. IoT-generated data can be monetized by businesses for insights and predictive modeling. So this real-time data monetization can also be a budding opportunity for IoT-based big data analytics and management. Example can be traffic data sold to navigation companies for data route optimization. So the keynotes to be taken from my today's presentation is that to fully harness the potential of IoT and AI, governments, business, and researchers must collaborate on standards, policies, and advancements. Investments in infrastructure, talents, and innovation, and deployment of IoT in large scales, especially in rural areas, are crucial for ensuring sustainable growth. Ethical considerations must remain at the forefront to build trust in IoT using AI responsibly. Nowadays, to being where we can utilize AI for utilizing where you can utilize this responsible AI for our responsible behavior, keeping in mind the ethical considerations for building trust in IoT ecosystems. So this is all about my today's presentation. I would like to welcome the questions from the participants, if any. Thank you for giving me this opportunity.
Thank you, madam. Thank you so much for that enriching topic regarding the big data on IoT, Internet of Things. So now I request participants to ask the questions regarding the session. Participants, if you have any queries, now it's the time to ask the questions. If you have any doubts regarding the big data analytics in IoT, you can ask the resource person, Dr. Parijata Majumdarji. I think the session is quite comprehensive and clear, madam. So that's the thing, the participant that doesn't have any questions. So now I request the coordinator of this FDP, Dr. E. Govind Garu, to address the gathering and to share the vote of thanks to the 6th day resource person, Dr. Parijata Majumdarji. Over to you, sir. Thank you.
Thank you, Ganesh. So on behalf of Avanti Institute of Engineering Technology and participants and from the organizers, now it's a time for vote of thanks, madam. Thank you for your valuable time you're spending here. It's my privilege to extend heartfelt vote of thanks on behalf of attendees for today's enlightening section led by Dr. Parijata Majumdar. So, Dr. Majumdar, your insights on the introduction to IoT and its importance in the data management and analytics set the stage of perfectly for understanding the potential and scope of IoT in today's data-driven world. From the exploring the IoT data lifecycle, including collection, transmission, storage, analysis, and visualization, to addressing the challenges in IoT data management, and your detailed explanation have been both thought-provoking and practical. Your discussion on big data analytics in IoT and contrast between the real-time and batch processing was particularly impactful and helping us grasp the significance of the choosing the right approaches for the specific applications. The introduction of IoT with big data and cloud computing gave us a clear picture of how these technologies work in the tandem to shape the future of the innovation. The session also provided valuable perspectives on the edge computing versus cloud computing and the transformative role of AI and machine learning in IoT analytics. Your ability to connect these technical concepts to real world cases studies from the smart cities to healthcare, industrial IoT, and predictive maintenance offered as a practical framework to understanding of their applications. We are immensely grateful for your time, effort, and expertise. So you have not only enhanced our understanding, but also inspired us to explore these areas further. Your ability to simplify intricate concept while keeping the sessions engaged has made this memorable learning and experience for all of us. I also take this opportunity to thank the organizers for arranging this impactful session and creating a platform for us to learn from esteemed experts like Dr. Majumdar. To all the participants, let us carry forward the knowledge we have gained today and apply it in our professional and academic pursuits. Once again, thank you, Dr. Majumdar, for our valuable contribution to this FDP. Thank you. Thank you, madam.
Thank you, sir. Thank you so much.
Thank you so much, sir, and thank you so much, madam. I'm filled with gratitude and admiration for the wealth of knowledge and insights shared during this journey. Each session has been a stepping stone in understanding the nuances of IoT and its integration with modern technologies. Allow me to take a moment to reflect on the highlights of this incredible learning experience. On the day one, Dr. Shankar Garu from Hindustan Deemed to be University has shared his insights on IoT in different domains like in engineering, in biotechnology, and in basic sciences, and its related project ideas and the case studies of different IoT domains. Followed by the second session. The second session is given by S. Ravichandran Garu, Dr. S. Ravichandran Garu from Bhimavaram, from DNREC Engineering College, Bhimavaram, has shared his views on the IoT security, which means the software IoT security and the threats that has been posed on the IoT systems. Followed by the third session, Dr. Mr. S. Sunil Kumar Garu, Managing Director, Unifirst Robotics, has shown and has given a deep insights on the real-time applications. He has shown some videos regarding the IoT in robotics. Followed by the fourth session, Dr. BKN Srinivas Garu from NIT Warangal has shared his insights, deep insights on the hardware security. So how security is so crucial for the IoT systems. And followed by the fifth session, Dr. Papiya Datta ji from BIET Hyderabad has shared her insights on 6G applications in IoT. how the artificial intelligence and the machine learning and deep learning can change the IoT systems in the environment of the Internet of Things. Now, the final session, which is given by the Dr. Parijata Majumdarji, has shared her insights on how the big data is very crucial in managing the IoT. How this IoT can be managed, can be used by using this big data analytics. So these are the main topics that have been shared by all these experts and the resource persons of this 6-day FDP. Now I request, now it is my honor to introduce a key figure who has been a constant source of support and inspiration for all of us throughout this program. We are fortunate to have with us today the co-patron of this FDP and the principal, Dr. C.P.V.N.J. Mohan Rao Garu, whose vision and leadership have played a pivotal role in fostering an environment, learning, and innovation at our institution. Without further delay, I request Dr. C.P.V.N.J. Mohan Rao Garu to kindly address us and share his words of wisdom before we proceed with the valedictory speech. Thank you, sir. Over to you.
Good evening, everyone. It is indeed a privilege to address you all as we conclude this enriching 6-day faculty development program on next generation Internet of Things. For the past 6 days, we have embarked on an incredible journey of learning, exploration, and innovation in one of the most dynamic fields of technology. The Internet of Things, as we all know, is not just a buzzword, it is shaping industries, redefining connectivity, and driving smart solutions to across domains. Through the insightful sessions, hands-on workshops, and thought-provoking discussions, we have had the opportunity to well into the potential of next-generation IoT technologies. I would like to take this moment to extend my heartfelt gratitude to the organizing committee, our distinguished speakers, and the participants who have made this program a resounding success. The efforts of our resource persons who shared their expertise and experiences have been invaluable in broadening our horizons. To our faculty members and participants, I hope the knowledge gained during this 6-day program empowers you to implement innovative teaching methodologies, integrate IoT concepts into your curriculum, and inspire your students to become the problem solvers of tomorrow. As we conclude this program, I encourage each of you to take forward the ideas and collaborations fostered here. Let us not be the end, but the beginning of a journey towards research, development, and innovation in Internet of Things and related domains. Once again, I thank everyone involved for their dedication and commitment. Together, let us continue to work towards excellence in academia and technology. Wishing you all success in your future endeavors. Thank you and have a wonderful day ahead. Thank you.
Thank you so much, Principal Sir, for such a kind and enlightening words regarding the session. As we conclude the session today, I hope all the participants have gained some knowledge regarding all the topics that have been covered throughout this 6 days FDP Faculty Development Program. Now I request all the participants to switch on your cameras so that we can take a group photo for a memoir. I request participants to switch on your cameras, please. I request all the participants to switch on your cameras. Thank you so much, participants, for your active participation in this 1 week faculty development program. I request all the participants to fill the day 6 feedback form to acquire the participation certificate. The certificate will be issued in another 3 days. All your certificates will be auto-generated by our email ID. So I request all the participants to kindly wait for 3 days to receive your FDP certificates. Now I request participants to fill the Google form for the final day of this FDP. And thank you so much. Thank you all. Namaste.
Thank you all, my dear friends, and my dear colleagues, and other faculty members, and other professors. Thank you for all 6 days you may be present, especially Dr. Navdeep Singh, Dr. Vijay Rani, Dr. Parijata Madam, Dr. Ramaya, and other faculty members of various institutes. Thank you for our support, sir. So within 3 days, we are sending all your certificates, and if any mistakes done by our FTP team organizers, or if any suggestions, so we need to provide, sir. So try to send our suggestions and improvements and everything through chat box and through WhatsApp. Thank you once again, and thank you everyone. Thank you.
Thank you, sir.
Thank you.
Thank you, sir. Thanks a lot, sir. It's really wonderful session.
Thank you so much, sir. I thank all the participants for your kind patience by listening to all these sessions. I hope all the participants have gained some knowledge regarding IoT. And if any doubts or if you want to know anything about all the sessions, you can ask us the questions and we can ask the resource persons to share the insights, or else we can share their contacts to you directly. Thank you all.